Yeah, Timothy, what did we tell you about being smart?
Being smart is not cool.
Okay, it's working now. All right. So, what many people might think is the most difficult problem on this assignment is the very last one, where you have an interconducting sphere and outer conducting shell, and you're told to find the electric potential Vp at point P. Okay. Let's conceptualize this so you understand the actual concept in addition to the mathematics that will allow us to get to the answer. Electric potential is the work per unit charge to bring electrical charge from infinity to a certain location. The electric potential will be the electric potential at that location. So that's what we said. We say the electric potential is equal to the negative integral from infinity to point P of E dot dr. And this is in general. Why is it negative? Because the electric potential will be positive. Let's say that there's an electric potential here. That's positive because I have a positive charge over here. Okay? When I bring a charge from infinity to this location, the path I take is this way. Right? It could be like this. It could be a zigzagging path. But because the electric force is conservative, is this in your way?
Yeah.
Because the electric force is conservative, I can, instead of saying, well, the actual path, which is some weird zigzaggy path, I can use the fact that it's a conservative force and just assume I came in a straight line. And so each dr, as I'm moving a little, let's call them a little test charge, Q, and each little dr is going to be a vector that points towards the location P, right? I do a little bit of work, E dot dr, an infinitesimally small amount of work to move it through each infinitesimally small displacement, dr. That dr is going to be this way. The electric field will always be this way if I'm dealing with a positive charge. Again, if it's a negative charge over here causing the field, causing the potential, then I might just flip everything. But if it's a positive charge, which is where the definitions come from, the electric field is in the opposite direction. Therefore, please understand this, because if you understand this, a lot of things get cleared up. Therefore, if I dot E and dr, well, that's E dr cosine theta. It is a scalar. The dot product of two vectors is a scalar. What's cosine theta here?
Well, theta 0, so it's 1. That's what I meant.
You all are wrong.
180.
What's the angle between these two vectors?
Negative 180.
It's negative 1. The angle is 180. So the cosine of the angle is negative 1. So E dot dr is negative E dr. But then that's why this negative is here. Right? Remember at first we defined it in terms of the work that you had to do to get it there? E dot dr in that case is positive. Right? But then the work done by the electric field, it reverses the direction of the electric force in opposition to your force. So the work it did was negative. And so I end up with a positive potential because that negative is constant. I bring it out and it cancels with this negative. What I like to do, because I don't like dealing with that negative, and we know this now, hopefully. Well, if I just flip and that's bringing the charge from infinity to point P. If I just flip the limits of integration and go from point P to infinity, now my drs are in this direction, right? Now each individual infinitesimally small dr is in the same direction as the electric field. When you flip the limits of integration, the negative goes away. And then I just have the electric field dotted with dr, and then it's positive, okay? So I'm going to use this. I'm going to use the definition, what's on the formula sheet, but then I do this integral by flipping the limits of integration just to make it a little less negatives to deal with, okay? The thing that you want to realize, though, this tells me the electric potential at point P. The electric potential at point P is technically a potential difference. A potential difference between the potential at infinity and point P. The electric potential at infinity is just defined to be 0. because the electric potential energy of an object infinitely far away from this charge. If I have this a charge here, and I have a charge that is literally infinitely far away, there's no potential energy, right? It's like lifting a weight and then taking it infinitely far away from the Earth. What's the potential energy of the weight relative to the Earth, or the weight Earth system? There's nothing there, right? So when you say the potential at a point, it's really a potential difference from infinity to that point, okay? Are you with me? Are you catching what I'm throwing at you?
Wait a minute, I thought we had to use calculus in this class, not pre-calculus. I wasn't prepared for this, whatever, like the trick question.
Okay. So if I want to know the electric potential at point P, I need to know the electric potential, or the electric potential energy per unit charge, or conversely what we just talked about, the amount of work per unit charge to bring an amount of electric charge from from infinity all the way to point P. Meaning to bring a collection of charge, it doesn't matter how much, because we're talking about the electric potential energy per unit charge, which is electric potential, from infinity first to point C, right? C is the radius of the outer radius of the shell. And then plus the potential difference, so that's the potential difference between infinity and C, plus the potential difference from C to B, plus the potential difference from B to R equals A plus B over 2. And I just add them together. Okay. What does that look like? Well, I'm going to write it like this. The potential at P is, again, the potential difference from infinity to point P. This isn't like the official way of writing this. This is just the way I write it to make it sense in my head. Well, that's going to be the potential difference from infinity to C. And remember, we're talking about the R values, the positions from the center here to where R equals C, plus the potential difference from C to B, plus the potential difference from B to A plus B over 2. So I'm going to have to find 3 potential differences and then just add them up. And that's why I'm doing this part, because we're going to do it 3 times, so hopefully it'll just get locked in your brain here after you see this a few times. And I'm going to do these one at a time, right? The potential difference between infinity and C. And again, you could write this as just being the potential at point C. When you just write the potential, it's assumed that you're talking about the potential difference between infinity and that point. Right, Alex? Right, Alex. Is Alex there? Oh yeah, he's there. So that's going to be, and again, on the formula sheet, it says delta V equals the negative integral of E dot dr. But potential difference, it's always the final minus the initial. So if it's final minus initial, it's the potential at C minus the potential at infinity, right? So you're going from infinity to point C. That's when I apply the fundamental theorem of calculus, I'm going to subtract the top from it. Or I can flip the limits of integration and go from C to infinity of E dot dr. I get the same result. Because if I'm going from infinity to C, the electric field points this way in both cases. Regardless, right? That's not going to change depending on how I'm going to do my math. The electric field is still there, pointing in the same direction. The electric field points this way. If I go from infinity to C, dRs, all those infinite number of infinitesimally small dRs are all pointing this way. So E dot dr itself is negative, so the negatives cancel and I get a positive potential. If I go from C to infinity, I'm going to integrate this way, right? I'm going to integrate this way, so E dot dr is in the same direction. E dot dr just gives me E dr, because the cosine of 0, they're both pointing that way, will be 1. So I get the same result here, either way. That's why I like flipping it. When I do this, I write this first because that's the equation on the formula sheet. I want to lodge that in my brain, but then I'll just flip the limits of integration and get rid of the negative. You don't have to do that. If you want to do it this way, that's fine. Just know that E dot dr will give you a negative E dr. And again, like if I'm looking at one of my infinitesimally small, my representative drs, you know, as I'm going from C to infinity, well, I have one dr that's here. And at that location, as it moves through that displacement dr, the electric field points that way. And so E dot dr
Oh, okay.
is just E dr times the cosine of the angle between them. Right?
Which now is 0, so it's positive.
Yeah.
Right.
Yeah.
Okay.
Does that make sense?
Yeah.
Can you explain the whole thing again? Just to make sure I get it.
Consult the video that I'm recording now after the fact.
Oh.
And we have an equation for E. We know the electric field. So I have equals the negative integral from C to infinity. It's just K times the charge responsible for the field, which by Gauss's law we know is just the charge contained within, or the total charge at the center of our Gaussian surface that we can draw. So in this case it's going to be both the charges, Q1 plus Q2. Because it'll act, what I meant to say, it'll act like a point charge outside of the spherical shell, right? It acts just like a point charge. So it'll be K Q1 plus Q2 quantity divided by the distance squared times dr. And then we can pull out the constants. K times Q1 plus Q2 times the integral from C to infinity. And when I do this integral, when I have a variable in the denominator, I like raising it to the negative power and putting it in the numerator. Makes it easier for my brain to see the integral. So that'll be then to pull out the constants times r to the negative 2 dr. So that's going to, and we expect this to be positive. We expect our answer to be positive because at this point, we have positive charge in here. We're assuming Q1 and Q2 are positive. So if the electric field points that way, I have maximum positive potential here and it decreases as I go that way. So when I do that integral, I get K times Q1 plus Q2 times, what's the integral of r to the negative 2?
Negative r to the negative 1.
Negative r to the negative 1 or negative 1 over r. Evaluated from C to infinity. So that's going to be K times Q1 plus Q2 times negative 1 over, I know you're not supposed to write infinity like it's a number, but we know that as r approaches infinity, this term right here approaches 0, right? Then minus negative 1 over C. And so when I work all that through, I just get K times Q1 plus Q2. This is then just going to be 0. Then minus negative 1 over C, so I get plus 1 over C, so it's just that. Right. So the delta V from infinity to C is equal to that guy. But that's not the whole story, because then I have to go from C to B. I can't just go straight through, because there's discontinuities here. Right? There's discontinuities in the expression for the electric field. We know that because we know the electric field is 0 within the spherical shell. And the electric field in here is due only to the charge at the center, Q1, by Gauss's law. So let's go ahead and do this guy. The potential difference from as I go from C to B. So as I take a charge from point C to point B, you might know this already, because we know the electric field is what inside here? 0. But we need to be a little more careful, so let's do the whole thing. That's going to be the integral, the negative integral from C to B. Yeah, as I'm going that way, from C to B of E dot dr. Or I can flip the integrals like I did here and go from the inner to the outer instead of going from the outer to the inner. You don't need to do this. So if I go from B to C instead, it'll be positive E dot dr. And then I know E dot dr is just K times the enclosed charge, times the charge underneath it, here's the deal. Here's the deal, though. How did I phrase it here in my notes? So here it's going to be K times the total charge divided by R squared dr, right? Where that's the total charge beneath, right? Beneath the point. So if I pick a random point here, how much charge lies below it? Because however much charge there is there, I can treat that as a point charge. So how much charge is below it there? What's that? Zero.
Oh, wait, yeah, it says something.
Right, there's zero charge. So just because the electric field, we talked about this, just because the electric field is zero, that doesn't imply the electric potential difference is zero, right? In this case, it is zero, because I know that there's zero charge. Like if I draw a Gaussian surface here, there's zero charge underneath it. And so the net charge below is zero, and so you get no electric field, right? You get no electric field, and you also get no electric potential. Why? Because the equation for electric potential, if I pull the constant out, it's K times 0 times the integral of r to the negative 2 dr. So it doesn't matter what this integral gives us, I'm multiplying it by 0. And so the potential difference from C to B is just 0.
So that's because it's a conducting shell, right?
Yeah. Because the charge is separated so that Q2 prime plus Q1 is 0.
Mm-hmm.
Yeah. Cool beans? I'm not creative like you, I just always do cool beans.
We're going to make you that t-shirt.
I'm expecting it.
Gaussian beam.
Voltaic beams.
Voltaic beans.
All right, here. I'm starting the list right now. The last page.
Okay. Now I want to go from B to A plus B over 2. So the potential difference between B and A plus B over 2, which is where point P resides, is going to be the negative integral from B to A plus B over 2 of E dot dr. You guys learn about that? I know I asked the other day, but I forgot. When you flip the limits of integration, you just put a negative in front and you're good.
Yeah, I learned that last year. Yeah, me too.
Everyone learned that last year?
And this year.
And this year?
Both.
Okay. So that'll just be the integral from A plus B over 2 to point B of E dot dr. And really, E dot dr, we know is just K times the charge underneath, you can think of, times or divided by R squared. So what charge is causing the field in the region between B and C? No, between A and B. What charge is creating the field in here?
Oh, Q1.
Q1, just Q1. Right? So it's going to be K Q1 over R squared times dr. I can pull the constants out again. Again, the calculus here is easy, right? The calculus in the calculus-based physics, most of it that we deal with is pretty easy. It's the whole setup and understanding the concepts that's difficult. So I pull out the K Q1, and then I integrate from A plus B over 2 to B of R to the negative second times dr. In fact, a lot of the calculus you learn, I've forgotten. I know the calculus I need to do AP Physics C and not much more. I used to know more when I was tutoring calculus, but I got tired of having to constantly, research and remember my calculus because it's hard, man. Calculus is hard.
It's a higher level class, isn't it?
Yeah. So, the potential difference then from B to A plus B over 2, well, I guess I'm just continuing. So that's going to equal K Q1 times, let me do that yet, times 1 over R, negative 1 over R, from A plus B over 2 to B. So that's going to be K times Q times negative 1 over B minus negative 2 over A plus B. Did I do that right?
what's up?
And you gotta flip it, multiplier it. Yeah. So that's just going to be negative KQ. Oh, this is Q1. This is Q1, sorry. Negative KQ1 over B plus 2KQ1 over A plus B. So that's the third result, my third potential. And then if I just add those together, if I just add those together, so the potential from infinity to point P is just the potential at point P, right? If you go from infinity, you can just call it the potential, right? When you say it's the potential, it's still a potential difference. It's just the potential difference between infinity and that location. Because the potential infinity at infinity is 0, then you can just call it the potential. That's going to be, and I just add these together. K times Q1 plus Q2 over C plus 2K Q1 over A plus B minus K Q1 over B.
I could have guessed that.
Oh man, I got it wrong. Dang it.
So is this the part where you're gonna say, okay, remember whenever we did these 5 pages of work, and then I'm gonna show you how to do it?
No.
with lines?
No, there's no way getting around this. This is the easy, yeah. This is the
This is the easy way.
yeah. I think it's pretty much the only way. It's not that the setup and the understanding. If you have that, the math isn't too difficult, right? What you want to understand is the potential at a point is equal to the potential difference between infinity and that point. If you have discontinuities, because if there's no discontinuity, then you just integrate this function, right? The E.dr function. But if there's discontinuities, then you got to integrate up to the discontinuity, then go from that discontinuity to the next one, and then go from the next one to the point. Right.
So the voltage, like, I guess at those discontinuities, if you're looking at it as like a graph in like relation to distance, would there be like, would it just be like a sharp turn, or would it be like just like an undefined open point?
Well, the potential. I guess if I'm going from infinity in, I got K times Q1 plus Q2 over R squared. So I think this would, you have a more potential out here. Well, it depends on the actual distances because we're just doing this symbolically. But yeah, it'd be pretty gross.
So it'd be kind of like jagged though at like the discontinuity points to where like you couldn't find or you couldn't integrate there, I guess. I'm
Well, even if you could integrate in here, you're so the charge,
zero.
the charge creating the potential at those points would just be 0. I mean, you could graph this, but you would need numerical values for Q1 and Q2.
Yeah.
But like if we're talking when you're between B and C, no, when you're between A and B, when you're between A and B, it's K Q1 over R squared. And so if you were like, if this distance here was the same as this distance here, the potential here is going to be higher than this because the potential here is due to Q1 and Q2. And if R is the same, then this potential is going to be larger than that potential would. But obviously when you get farther out here, it's going to go down. Yeah. So if I was graphing something like that, let's just say it's along the x-axis, it would be, it wouldn't be 0 inside here.
But it's a conducting sphere, so it would be zero.
Oh, it would be, yeah. I'd have to think about that more. Stop making me think.
Okay.
We'll come back to that.
Jeez.
We'll come back to that. Yeah. Okay, so I apologize for taking up most of the class with that, but this is one that you probably would have struggled with quite a bit. So, there you go.
I guessed it first try.
Well, if you guessed it, good for you.
Guess is law, right?
Guess is long.
Law.
All right, everyone home. Goodbye.